Okay, so now we will show that a special case of division can be done in NC1. Okay, so given an n bit integer x and a m such that m is less than or equal to n. That is what I have, right? Given when the following are in log space uniform NC1. What are they? The first one is computing x mod m. Second is computing x divided by m, and the third is computing x inverse mod m. Okay. Essentially what it is saying is that if the divisor is small, okay, if the divisor is m is less than n, so m is essentially a log n bit number at most, okay, then we can actually do division and all these related problems, that is division, computing the remainder of x inverse in NC1. Okay. So why is this important? Because next class what we will show is that the actual problem, that is if I have two n bit integers x and y, we can actually break it up into smaller divisions where each of the divisors are small. Okay, each of the divisors are some log n bit integers. Okay, so clear so far? So what we do here is that, so as I said, observe that, well, m is much smaller compared to x. Okay, so x can be as large as 2 to the power n, but m is only at most n. So what we will do is, the first step of the proof is to pre-compute some things, okay, pre-compute some quantities which are independent of x and m, okay, which only depends on n. So what we will do is, we will, well, actually it will depend on m, but okay, I will just come to that, yeah. So how do I denote this? So pre-compute these quantities a to the power I, which is congruent to 2 to the power I mod m. Okay. So once again note that because m is small, I can actually do this computation for each and every m. There are only polynomially many m's, different m's, right, from 1 to n. So for each value of m, I can do this computation in parallel. Okay, for m equal to 1 I can do this, for m equal to 2 I can do this, and well, I will only need this for 1 m, but it does not matter to me, okay, because I can do this. And what is this computation? It is just saying that for each power of 2, what is the remainder of dividing 2 to the power I by m. Okay. So I do this computation. And so what do I mean by pre-compute? What I mean by pre-compute is that you can actually do this in log space. You do not have to do this in NC, because you are not using the power, you are not actually reading the input over here. Okay. So you are just, this is a quantity which is independent of the input, okay, which will be the same for all x's of a fixed length. Okay. So you just do this using a log space machine. but that is what I am saying. So, m actually does not matter, because m is so small, m is just log n bit. So, you can actually do this for each and every m, right. So, you can do this for each and every m. So, you can think of it as follows, that for each and every m I have a different circuit. Yeah, maybe you can do this in NC1 also, but does not matter. I will do this in very easily. I can do this in log space. Okay. So, now what we will do is we will compute the following. Yeah. So, we will compute I do not have a y over here, right? Yeah. So, I will compute y, which is equal to sigma ai xi. Okay. Let me just write this over here in bracket, that let x be the bit string x n minus 1 up to x 0. Okay. So, x is this bit string. So, when I say xi, I mean the ith bit of x. So, I compute y, which is sigma I equal to 0 up to n minus 1 of this. Okay. What does it mean? So, it means that y is so these AIs are congruent to 2 to the power I mod m, which means that these y is also congruent to x mod m. Okay. So, why is this? Why is y congruent to x mod m? Because actually what is x? Okay. So, another way of looking at x is nothing but sigma 2 to the power I xi, right. So, this is basically the number x. Okay. So, here instead of 2 to the power I, basically I am taking mod on both sides, mod m on both sides. So, on the left hand side, so on the right hand side I get x mod m, and on the left hand side I get this quantity y. Now, how large can y be? So, note that well, a trivial upper bound is that, so y has n many summations. Okay. So, and n, so actually n minus 1 many summation, and well, in terms of m, this quantity is, I mean m is can be as large as n. Okay. So, it is m minus 1 times each of these AIs again can be as large as m. Okay. Actually, yeah. So, actually, okay. So, this has sorry. So, what I mean is that so the number of terms here is at most m, and the value of each AI is at most m minus 1, right, because it is a remainder modulo m, and of course it is greater than or equal to 0. So, each xi is either 0 or 1. So, yeah. So, this is the value of y. So, now what we do is for every t from 0 up to how long do I want to go? M minus 1, compute y minus t of m in parallel and what do I want to output? Yeah, y minus Tm such that that particular y minus Tm is greater than or equal to 0 and less than m. Okay. So, actually this is very simple. The idea is that I have to compute x mod m. Okay. I reduce it to computing division with respect to y, okay, where y is a small number. That is essentially all that I am doing over here. So, from x I am reducing the problem to y and I am proving that x mod m is the same as y. Now, I just have to check for each value of t that what is the largest value of t such that y minus Tm is between 0 and m, okay, and essentially that y minus Tm is my remainder. Okay. So, y and x are both congruent to both congruent modulo m. So, essentially I have reduced the problem to y from x and now I am just doing this with respect to, so basically now I am doing it for each and every value of t, because I know that y is small for us, y is no longer large. Okay. So, now moving to the next part. So, next part is again something that I will just kind of leave as a small exercise, but so once we have the remainder, how do we get the quotient? Okay. So, note that if I have a remainder, okay, so if z equal to okay, fine, z n minus 1 up to z0 be equal to x. So, this is a number x n minus 1 up to x0 by 2 by m, then the ith bit of z is equal to 1 if and only if twice of x I plus 1 n minus 1 up to x I plus 1 mod m plus xi is greater than or equal to m. Okay. Okay. Is this correct? Yeah. So what are we saying over here? So this is actually nothing but how long division works. Okay, so essentially how I get each and every symbol of the quotient. So when I am doing long division, okay, so let us say I have a number x1 to xn minus 1 to x0, it can be over, actually this can be over what do I say, I mean it need not be even a binary number, okay, it can be over any array, it can be any k array number, it can even be decimal number, but there instead of 2 you will have whatever k you are considering. But let us say you have some binary number and you want to divide it by m, okay. So the way that thing produces is that, so suppose the quotient that it produces is some zn minus 1 to z0, then the ith bit of z is 1 if and only if this is true. Okay. So basically the way it works is that you keep on looking at the difference between whatever is the product of the ith bit and your divisor, okay, you bring it down, look at the next bit and so on. So this is essentially formalization of that idea, okay. So you can verify this yourself, okay, you can actually go back and you can prove this. This is very simple, this is just same thing that you have learnt in your school, okay. So now once we have this, division is actually quite simple, because I have to output the quotient, and note that outputting the quotient is nothing but computing a modulus. Okay. So the Zi is equal to 1 if and only if twice xn minus 1 up to xi, I look at this number, okay, so this smaller number, do modulo m, add xi to it and compare it with m, and well, if it is greater than or equal to m, then Zi will be 1, otherwise not. Okay, so I can do this for each and every I in parallel. Okay, so the algorithm is do the above computation in parallel for every I, okay. And that's it, and then you get the value of Zi. So the last one is also similar. So x inverse mod m is equal to, let us say, some value u if and only if is well, okay, it's equal to u if and only if xu is congruent to 1 mod m, okay. So I want to output u over here, u is at most m, yeah, so I just do this check in parallel, okay. So algorithm is that for all u check in parallel if x times u is congruent to 1 mod m. So multiplication we know is in NC1, and just we saw that this also is in NC1. Okay. So that's it. So what we are going to see next time is the following. So we'll have to try to generalize. Okay. So all of this is with respect to a small number x and a small number. Now, how do we generalize this to a general y? So, what we will prove next time is the following result. So, given an n bit integer x and a prime power p to the power l such that p to the power l is at most n. No, sorry. So, given not n, so we will show the iterated product here. So, given n bit integers, okay, let us say x1 up to xn and a prime power p where p to the power l is less than n. Computing the iterated product of x to the power I mod p to the power l is in log space uniform NC1. Okay. So, as I was saying is that ultimately our agenda is to show that we can do this computation in NC1, okay, even in general, okay. So, even without taking modulo a power of prime, but what we will see before that is that if we have a power, if we have a prime power and if you want to do iterated product modulo prime power, that is actually doable in NC1. Okay. Okay, so I will stop here. So for the general proof, we will actually, as I said, we will break it down. So given any exercise, we will actually break it down into smaller things using Chinese remaindering, so that you can actually represent it in this form. So this is where the number theory will actually come in.